Hey everyone, we have Christy Lay Minehan here. She'll be doing a talk on the nuance of the nonce, data analysis of the blockchain. She has a really amazing background. She was the former CTO at Core Scientific and also was at Genesis Mining, and now she's the CEO of Oh God A .co, I believe. So, Christy, would you mind speaking, and then we can get the audience to confirm that they can hear you?
Yeah. Hi, everyone. How are you all doing? No parrots today, sadly. They're outside enjoying the sunshine. So it seems like we're good and everyone can hear me. So are we ready to start? Awesome. So I wanted to present today some of the research that I've been working on for the last few weeks. Originally, we wanted to take this take this talk down a different track, but some interesting things happened in the blockchain ecosystem, and we were curious whether some of our models and theories could be put to the test. So let's get started. So first, before we get into all the fun technical stuff, we really have to go through the boring stuff of defining what is a nonce. And well, if you're Australian like me, a nonce has a different meaning. But for the rest of the blockchain mining ecosystem, a nonce is really this pseudo-random number that's utilized as a counter. And nonces are really interesting in that, there's only one winning nonce, one golden nonce, where with a SHA-256 hash, it can craft a valid block. And in theory, all nonces should be entirely random, meaning no nonce value should have, any more higher chance to be a golden nonce. And so from 2010 until 2016, this theory proved to be true for Bitcoin at least. However, in May of 2016, four distinct white bands started to form over the Bitcoin mining network. And in 2019, 100 trillion USD actually caught this and made a bit of a tweet about it. And this started a lot of analysis in the space and a lot of interest around what other signals could be hiding in the blockchain data. Now, what's interesting is this signal actually directly corresponds to the announcement date of the Bitmain S9 and also the shipping date of mid-June. So here where it's just starting, that's when Bitmain's made their announcement. And as it gets stronger and stronger, they've started to ship, and then this is until present. So it was pretty interesting to find this. After all, why would miners actually care which nonce is the winning nonce? Why would they be discarding some of these nonces? And so 2 days later, someone found this for the Monero blockchain and did an analysis. And this we now know to be the rise of the very first ASICs that were on the Monero blockchain. And then the second wave of ASICs that hit the Monero blockchain. And then later, Token Analysis did a breakdown by pool, where we could clearly see the distribution per pool. And later on, this was broken down very clearly between pool. So notice that any sort of Bitmain affiliated pool has very strong banding, which corresponds to the 4 hash boards across an S9, whereas F2 pool is quite, a bit distributed. Slush pool still has the banding there, but it's getting fainter. And of course, the smoking gun to this theory is Bitfury's own pool, where Bitfury's miners do not have this pattern, do not search the nonce space in the same way that the S9 miners do. And of course, we correlate it with the overt ASIC boost to see if there was any kind of pattern lining up with that. Now, of course, Bitfury's miners at the time were also capable of ASIC boost. So it seems that this graph really just represents, that Bitmain's miners just had a higher proportion of the network, thus they were mining most of the overt ASIC boost blocks. So we were really interested with all of this research. And early this year, we thought, well, hang on, what if you could actually fingerprint individual devices with this data? And so we decided to test out our theory. We tried it at first with the Ethereum network. Now, when we did this, originally, no obvious signal appeared. It appeared that the winning nonce distribution was pretty uniformly sorry, it was strongly uniform. You see some banding here, which kind of correlates to first the CPU mining phase of Ethereum, and then eventually a bit of the GPU mining phase, but they only represent a very small proportion of mined blocks. Thus, they're not really an interesting signal for us. However, if we analyze all 64 individual bits fixed within the nonce, some really interesting patterns begin to emerge. Now, later on, we realize that this can be due to a number of factors. Sometimes it's due to the hardware makeup, sometimes it's due to the software, or sometimes it's due to pools. And so in our earlier report, we were able to pinpoint not only the E3, which is an ethash ASIC miner, so the E3 signal, or fingerprint as we call it, which this top band up here represents when the E3 was up until the point where the E3 was announced. And then this second blue stripe here represents when the E3 miners actually started shipping and were mining. And this middle band here is quite prevalent in all of ETH analysis, and we'll get into what that actually is in just a moment. So turns out that that giant middle band is actually the fingerprint of Claymore. And what was really interesting is we could literally see in the chain data at the moment when Claymore released his version 15 of his miner, how the bits steadily became more and more fixed across 30 to 33, bit 30 to 33. And so it's pretty prevalent in mining software for them to fix a certain number of bits. So Claymore's signature is showing up because software picks a random value from the top 4 bytes, and then it's linearly searching the bottom 4 bytes from 0. So it infrequently has to change the top 5 bytes, thus you're getting a bit of extra efficiency in ethash mining. Now, some other mining software has adopted this same strategy, but what was interesting is Claymore was also potentially using this to track dev fees. In other words, he wanted to see which proportion of blocks were mined that had his winning nonce signature in it, and was he appropriately getting dev fees for that? So he could do some cost-based analysis of whether it made sense to keep developing mining software. So then we had the idea, given the recent Ethereum Classic attack that just happened this month. We were like, well, hang on, what if we took all of the research we've learned, all of the data analysis that we've been building tools for, and tried to apply it to the Ethereum Classic attack? And we were quite surprised at what we were able to find. So I'll give a really quick summary for people who aren't familiar. Ethereum Classic is a fork of ethash and has had some troubled history with 51% attacks before. Recently, it was hit by 2 51% attacks. So one on July 31st of this year, and then one on August 7th, 2020. And it came from the exact same attacker as well. So the BitQuery released a fantastic report that breaks down this attack, which I encourage you to go and read. And essentially, what we know is that all of the a majority of the hash rate for the attack was rented from NiceHash, and then the cost to launch the first attack was quite cheap. It was only 200K, and he made away with a profit of 5.6 million. Whereas on his second attack, it was a cost of around about 180K. 172 to 180K, and he only managed to escape with a profit of 1.7 million before exchanges shut him down. For those of you who don't understand what a 51% attack is, it's not just having a majority of the network hashing power. It's also having the ability to mine on your own private chain. We often call these shadow chains, and try to get ahead of the main chain. At which point you then broadcast your chain, and it becomes the source of truth, because proof of work consensus simply tolerates the longest chain. It assumes that is the valid chain. So then we thought, okay, well, let's start looking at the nonce data. And so BitQuery had provided all of the addresses mined during the attack, so it was really simple for us to extract the attacker's blocks. And so this right here is just a overall view of 2020 for Ethereum Classic of its nonce values versus its block timestamps and all of the different address data. Now, at first we were hunting for the extra nonce used by NiceHash, and since we were getting all of our queries from Google's BigQuery, all of our data from Google's BigQuery, we thought that, the extra data field was what we were searching for, the extra nonce field. Turns out we were incredibly wrong on that, but we found something even more interesting. So there's this field in Ethereum Classic, and we'll get into what that means. It's in all hash-based proof of work currencies. Extra data is quite fascinating. And what all of the reports seem to have missed is that every single block from the attack, as well as all nearby blocks up to 24 hours before the attack, had the exact same extra data value that has never been used in the history of Ethereum Classic or on Ethereum. That was pretty interesting for us. So we wanted to jump in further. And to explain this graph a little bit before we jump on, so this cyan here, the banding pattern you see, is specifically the fingerprint of the known attacker addresses. But this, sorry, the magenta, but the cyan one you see here, this is a suspected attacker address. So this is one that has the same extra data as the attacker blocks, or that is somehow correlated to the mining addresses used by the attacker. So then we decided to isolate these attacker addresses a little bit. And so in red again, we have the known attacker addresses that were listed on BigQuery. In cyan are all of these different addresses with the unique extra data field. And so we can see that this particular attacker was actually mining with this extra data field all the way up until January 2020. So he was prevalent on the network for quite some time. So both address sets represented a substantial amount of hash rate during and after the attacks. That's what you see here, right in the middle, where you see the big clustering of red. Now, what's interesting is that the suspected attacker address, which used that same extra data content, has been a consistent part of the Ethereum Classic network. We found all the way back until 2017. And he's represented on average 2.5% of the net hash. And so for this presentation, we've really just done a snapshot of the exact month. But as you start looking through historical data, he has been quite prevalent. He's always had at least, probably about 100 to 200 rigs on the Ethereum network. He's never taken it off. We see no evidence of a nice hash fingerprint. So it means that he's probably a frequent contributor or a frequent, passionate miner of Ethereum Classic. This was interesting for us to find. So then we decided we're going to go do our regular nonce analysis and see what could happen. So when we look at the nonce bits that are fixed either to 0 or 1 proportionally over a weighted time average, there's not really an obvious pattern. We can kind of see some banding here in the middle. It's not too obvious though. Kind of see some artifacts here in February 2020. Can kind of see something here, just still not obvious. However, with a little bit of magic and an adjustment to our x-axis, with a weighted block weighted average, we now see that the upper 6 bits are being clustered to get together. So NiceHash has a very unique signature for most mining, where it fixes the upper 8 bits, essentially to allow you to use the service. For whatever reason, in this specific attack, only the upper 6 bits were used, but you'll see this continuation of NiceHash's fingerprint across any kind of blockchain where they offer their services. So it's a really great way to track NiceHash's amount of hash rate. Now, the middle banding patterns for us were really interesting. So they have a differing amount of fixed bits from our previous F analysis, and they differ from the ETC average for the same time period, meaning that our attacker was either using hardware or software that fixed bits 28 to 40 instead of the standard bits that most other mining software fixes. So then we decided, well, could we go back to the 2019 attack when Ethereum Classic was 51% attacked back then and see what we could discover? And of course, the pattern in the nonce values for the first 51% attack isn't, isn't as distinct due to a much smaller scope. But we see in red here the very characteristic banding of nice hash again. And of course, now we know that the attacker did rent out nice hash rate. And again, we do another bit of an analysis. And oh, look at that. That's quite interesting. So again, here in the middle, we see that the middle banding is consistent with the same software the attacker in 2020 used. So we're not sure which software fingerprint this is yet. It could be Phoenix Miner. It could be something that's not yet on the market, but we do see that it is the same exact pattern. And here, even though it's a little stretched out, and sorry for that, it's just how the graph is presented, but we have the distinct banding of nice hash, again, in its upper 6 bits. So let's talk a little bit about extra data and why this is so interesting and why the attacker did this. So in order to pull off a shadow mining attack, you don't just need to have a majority of hash power. You need to have nodes as well to broadcast your transactions. And so what the attacker would have had to have done is he would have had to run his own nodes, and he would have had to identify his individual blocks in some way to know they have been broadcast to the main network and accepted by the main network. He only had a very small window of opportunity to pull off this attack. This is where the extra data field comes in handy. Most block explorers will discard this field. It's only been used once in Ethereum's history for signaling for PROM-PAL, yes or no. So it's really just a signaling vote. The attacker put a random Ethereum address that is not valid, just sitting in there, and he's used that to identify his blocks. And this way, when he's pushed all of his work to the main chain, he's been able to quickly identify, hang on, I'm now the most legitimate chain, and he's able to go and execute his series of attacks on exchanges to split off his double spend. Now, this is where the attacker is really messed up. Because he's fingerprinted himself on the nodes, you're able to gain even more analysis from this. We can tell quite a lot from the node software about location, about what exchange was used, even things from timestamps. So whenever you need to perform a shadow mining attack, you do have to have your own node set, meaning it's pretty easy to trace you if you have the right tools in place. So extra data is really, really fascinating. Bitcoin has a similar field. Most cryptocurrencies out there do have a similar field. We've performed similar research over Library blockchain, the SIA network, Zcash, and Zcoin, and all of them have very interesting patterns. Some miners will put in worker IDs into the extra data field. Some pools will use it for debugging data. We know that F2 pool does this oftentimes with their Zcash transactions. So it's usually just a diagnostic field. And this, of course, reduces miner anonymity quite heavily. So what did we learn from this attack? Well, we learned that the suspected attacker only goes back to blocks mined in 2017. So he's been on the network for about 3 years. The unknown attacker address was really just a once and done. So it was just created for this attack and then thrown away. The suspected attacker is always associated with this extra data field, which has its unique value inside of it, or any addresses that were associated with this with that attacker. And he has today 2.5% roughly of the net hash of Ethereum Classic. So he is quite an active miner. And further research into his specific signature can tell us which software he was using and which hardware he was using. And remember, when I say suspected attacker, this means he has his own mining farm. So he had to rent out enough hash rate to perform an attack, but he still has hardware of his own. Now, if we correlate nonce analysis with other kinds of data sources, stuff like exchange data, timestamp data, even some wallet analysis, then all of a sudden, anonymity of this particular miner is decreased. We can then do further analysis of the blocks and nodes which broadcasted these very specific transactions that led to the double spend. And you can reveal a very approximate or general location if he hasn't carefully covered his tracks. Then you can correlate it with exchange, buy, sell flow from the suspected attacker, which we're working on today, and we're super excited for the results that we've gotten from that. And what's really cool is you can cross-reference this with utility bill schedules. So what I mean by this is miners generally have buy-sell strategies that are kind of consistent depending on where they fall in the stack. So your enterprise public company miner might have a different sell schedule to your home miner, who's really mining and then selling quite a large amount for electricity. And so if we were able to figure out when utilities were often paid during the dates where he executes frequent sell orders, because remember, we have all of the blocks he's mined from 2017, then we would get a much more accurate understanding of what power grid the attacker was linked to, which is pretty cool. Now, what we're planning on doing for this, whole nonce analysis and what could actually be opened up is a few things. So winning nonce values and bit fixing, so where you're fixing specific bits to either 0 or 1 within the whole nonce, can give information about your worker ID, your pool diagnostics, and your hardware type. Search strategies for winning nonce differ not only from the hardware type and software type, but also across different coins. What I mean by that is, the tooling that you use to analyze nonces in Bitcoin cannot be used on Ethereum. So it's just entirely different. And the search strategies for a Bitcoin mining pool will drastically differ from, say, a Monero mining pool. Winning nonces can also be weighted. And so in our original Ethereum port, this was one of our achievements. We built a quantitative model that was able to assign a number of units, meaning I could figure out how many GTX 1080s you have as an individual miner, just based upon your distribution of winning nonces. And this can help bring a lot of transparency to the ecosystem. Why is that important? As specifically Bitcoin mining becomes more and more industrialized, and more analysis comes and scrutiny comes around hardware manufacturers, it's really important to understand the total number of deployed units on the network. So this is something that the research can reveal today, which is quite interesting. And by fingerprinting NiceHash's nonce signature, we're able to accurately weigh the percent of rented hash on a chain. So NiceHash has a terrible rap in the ecosystem for causing all of these 51% attacks. I have a differing view on this, but essentially, if we can accurately fingerprint NiceHash's signature, and it's consistent across all chains, they always just use those top 8 bits, then we're able to, really figure out what percent of rented hash sits on any given blockchain network. So bit fixing, why does that happen? Well, it's incredibly beneficial to hardware manufacturers to keep an eye on their number of units deployed. So say 5,000 units, leave Bitmain's warehouse. And then over time, some of those units fail, they degrade, they go out of commission. How does Bitmain know when to replenish supply, aside from just talking to customers? Well, a great way is that at any time, they can just check the blockchain and see how many number of their units are mining based upon the distribution of these winning nonces. Now, nonce search strategies can be disguised, but they're often a side effect of a hardware implementation, which can't be fixed, or a proxy. I do know that some FPGA developers have actively tried to hide their search strategies, but the reality is that you leave quite a few optimizations on the table, and eventually, across a wide enough data set, patterns are going to emerge. It's just a rule of data science, actually. And so winning nonces can be analyzed to look for these new and emerging hardware types, which is how the first Monero ASICs were actually discovered. And you actually only need more than 10% of the hash rate, but with our quantitative model we developed for the Ethereum network, they can actually have less than 1% of the network hash rate, and you can accurately detect if it's a unique hardware type. And so again, if we could fingerprint this kind of mining software, so if we could see the distribution between Claymore versus Phoenix Miner versus T-Rex Miner, we'd gain really valuable insight into kind of client breakdown. All right, and so any questions? And I assume that there is quite a few. So Santiago, you asked if the attacker is watching, can't they just change hardware / bit focus? Sure, they can. It's just a lot of work. Quite frankly, I don't think most miners are aware that this is actually a pattern that exists. Pools don't want to change it because, as I mentioned, it's really a diagnostic effect. So if you want to change it yourself, you really do have to run your own pool, your own infrastructure. Now, someone that's renting from NiceHash, chances are they're not going to have the ability to modify their own bits as well or get rid of this signature. And in the case of Ethash, you really do want that very distinctive banding when you're GPU mining. You gain about it's close to a 1.5 to 2% efficiency just by doing that specific search strategy. And so oftentimes it's always a trade-off. Do you want complete stealth or do you want to get, the most hash rate possible? 9 times out of 10, an honest miner is going to choose, the efficiency gains. Now, of course, if an attacker hides this, great, but chances are they're going to let other bits of data slip. So this is just one more point in sort of like your blockchain data analysis. You should always correlate it with wallets and exchange data. And so Nate asks, aren't the bans in the nonce distribution areas where the search is less competitive? That is, if you were to build something to target these bans specifically, wouldn't you outperform on a return on hashing power? So it actually depends what blockchain you're talking about. So Bitcoin's, and this is why I said that the tooling isn't really cross-relational. So in Bitcoin specifically, those bans that you see are actually discarded, meaning the mining software has, or in this case, the S9s, have decided to just ignore those non-search spaces entirely. This is due to an artifact actually in the hardware and how the hash boards are laid out and how work is distributed between the ASICs. Now, on the Ethereum network, in that case, your bans are really where nonces have, specific bitses have been fixed to 1 more often than just 50-50, or 0 more often than 50-50. So it has nothing to do really with the target. It's due to the fact that for whatever reason, they're fingerprinting and always fixing those bits across their specific winning blocks. So it has nothing to do really with competitive search. Shannon asks, how much harder would a 51% attack on Bitcoin be? I mean, I'm not an economist. There's been some fantastic people that have written about the economics of 51% attacking Bitcoin. Bitcoin is too big right now, I really believe, to be 51% attacked. I mean, at this point, you have close to 12 to 15 industrial players. None of them want to see the network damaged in any way. It would be quite expensive. There are some tools out there that can give you sort of the estimated number. I can't tell you off the top of my head, but it's not very feasible. What's interesting to note is that many people think you need 51% of a network. You only really need like 43% and enough nodes and speed. So it seems like today to do a 1-hour attack on Bitcoin, it's only 650K. So that's actually pretty achievable if you wanted to go through all of that effort. So Santiago asks, can you elaborate on correlation with power consumption? So yeah, very specifically, what I mean is the utility bills. So let's take my utility bill. I have my electricity due on the 15th of each month. And so then if I'm a miner, I will then go and sell a certain amount of my Bitcoin to pay for my electricity. Now, my utility bill here in Seattle is different from, say, China's utility bill and the monthly billings on that. And so each region usually has kind of a congregation around utilities, when they're due, when they're paid. What is interesting is that if you can watch over a period of a year when a miner actively sells monthly, and there are patterns in this, you can pinpoint, okay, that's probably when his electricity bill is due. And then if you cross-reference that with a list of worldwide utility companies, and when they often collect billing from their customers, that gives you an even better data point. So essentially, if I see that the known attacker is always selling on the 25th of every single month, I'm going to assume that is, he either contingent with his USD conversion strategies, or it's contingent with his utility bills. And he has monthly expenses he has to pay. It could also be hosting, and so that is another data point that you could add into it. Shannon asks, are there open source tools one could use to scrape nodes and peer information for the Ethereum network? Yes. So Google's BigQuery is fantastic. So unfortunately, there is no what we call a block extractor, meaning you'll have to write your own little extractor tool to just grab data out of the data set BigQuery gives you. But Google runs, an Ethereum and an Ethereum Classic node, and you can perform this research on your own. If you can reach out to me on Twitter, I'm happy to give you a sample block extractor as well. This has been done many times over. During the course of this particular research, we actually found some fantastic tools other people have built. There's the Pool Detective from MIT. There is the Pool Explorer that's coming out from MIT as well. There's similar tools that have been built just recently, such as ForkWatch, looking for 51% attacks. So there's a lot of different tools out there. Usually they're API based. In some cases, they will have a charge associated with them because you have to pay for, the constant pull push queries. But I really do recommend just using Google's BigQuery. It's great. And if you want to get into the smaller chains, then you'll just have to run your own node, and then you just adapt your block extractor to get all of that data out. And yeah, Santiago, the final question from Santiago, or I guess the statement is, a nation state could do a Bitcoin 51% attack and use shorts to hedge the costs. Yeah, and a nation state could do that. Honestly, the TAM of a cost on Bitcoin is a little too low for a nation state. I mean, they have their focus on other things. Oftentimes when we have these theoretical attacks, it's really helpful to apply logic and think about how realistic is it? How realistic is it that the United States is going to go and perform a 51% attack on Bitcoin and escape with what? Maybe 50 million, 60 million before exchanges shut down everything. And as a network evolves, and as it becomes older and older, it becomes more and more resilient to 51% attacks. So a great example of this is actually Ethereum Classic. It's been 51% attacked almost 3, maybe 4 times in the last 2 years, and it has done nothing to the price. The price has just remained stable. We're also starting to see this in Bitcoin Gold. The market just isn't responding to 51% attacks that much because the exchanges are handling most of that burden. Yes, I agree. Undermining the movement could be a goal, but I think with all of the advancements we're starting to see, at least in the United States, most of the world understands Bitcoin is here to stay, and understands Ethereum is here to stay. They don't want to undermine those networks. Smaller networks, you could think about some of these theoretical attacks when it gets into private blockchains. What if I wanted to go after the government of Georgia's private blockchain and their data? Since they're, for those of you who don't know, I believe it was Bitfury did a joint venture with the country of Georgia for putting some records on the Bitcoin blockchain. So, which was interesting and also innovative for its time. All right, guys, any other questions before I jump off? Sorry I talked your ear off.
Cool. So we're going to take a short 15-minute break, and we're going to start talking about energy grids outside of China next. Cool. Thanks, Christy.
Perfect. Have a great one, guys.